All right. Is that everyone turned in?
Is there some kind of group technique that I didn't know about? My table's here.
Is that it? You turn in? You don't need the date, but yeah, it's 21st. All right, so for the first one, if we write this in sigma notation, it's going to be 1 over what? N times the cube root of n, right? Which is, the bottom is n to the first power times n to the 1/3 power. And you add those, that's 4/3. Yeah, you'll still get it, but that's 4/3, right? And this is p series. This is p being greater than 1, which means it converges, right?
That's it, right?
That's it. That's it for that one, okay? Now the second one, now you could have maybe shown it a different way, all right? If you did, fine, but it probably took you a little more time. On the second one, I want to compare it to something, all right? And if n is really big, then this one doesn't matter and this one doesn't matter, right? So let's take a vote. How many of you compared this to 1 over n squared? Anyone do that? Yeah? What did you use? Would you, constant. You put 3, right? You put 3. Let's look at this. If you just use this versus this one, okay? This is a very good example to demonstrate something, all right? If I try and compare this, sorry, not n squared. I meant to say n. I apologize. Yes. Right. Because when this is really big, this really looks like n squared over 3n cubed, and that's really 1 over 3n squared, or 3n. I keep on wanting to square it, right? But, okay, so let's see. What if you say, well, that's close enough to 1 over n, and 1 over n diverges, right? So this is divergent. Let's go with this one first. This is divergent, so I'm comparing this to a divergent series, right? So what I have to show is I want to show that a sub n is always what? Greater than or equal to b sub n. B sub n here is 1 over n. And the other one was n squared plus 1 over 3n cubed plus 1. And if you cross multiply here, right, n times this, you get n cubed plus n greater than or equal to, then here and here, 3n cubed plus 1. Yeah, this isn't going to work. It's not going to work. Okay, now here's why it's not going to work. Let's move this n cubed over. You get 2n cubed plus 1 is less than or equal to n, right? I mean, just looking at that right there, that should tell you that there's no way. Because if n is 1, this is bigger than this, right? If n is 2, n cubed, 2 cubed is going to get big, plus times 2 plus 1. That's bigger than 2, right? Yes? I saw what you did. I'll talk to you about it afterward. So this is not going to hold, okay? The problem, now this is where we want to recognize where we had an issue if we did it this way. The problem was that when we did the cross multiplication, I just got an n cubed here, right? And that made this side smaller than this 3n cubed. It would have been really nice had this been what? 3n cubed, then they would have canceled. Or 4n cubed, right? That's fine. So instead of comparing it to this, compare it to this. That's still divergent because the constant down there can be pulled out, right? Compare it to, you want 4 or 3? I think most of you did 3. 3 here, 3 here. And now when you do your cross multiplication, this becomes 3 and this becomes 3, right? Then these cancel completely. And you get 3n is greater than or equal to 1, which is true. Okay? So when I grade these on your test, right, what I'm looking for is not this isn't, I mean, because this is really like a true or false question, right? There's two possible answers, divergence or convergence. I'm not looking to see necessarily did you get the right answer, because that's almost a 50-50. You can make a mistake and still get the right answer. I'm looking for the work. You have to show it, right? Okay.
If we don't put like the want to show part, like I did the work correctly, but I didn't put like want to show.
Well, on the quiz, I won't care so much. On the exam, I want you to start getting into the habit of writing down your ideas logically. Okay? That's going to serve you better down the road.
Like I did all the work like you did there, and then I drew like I did like a therefore since.
Yeah.
But I didn't put the want to show.
That's okay, as long as I need to know what you're doing, right? Okay. If I can tell by looking at your work what you're doing, then we're good. All right, here we go. We're going to move on. Given some infinite series, we are in 8.4, okay? We're moving into 8.4. This is called other convergence tests. So far on our list, what have we talked about in detail? We've done integral test, comparison test. We talked a little bit about ratio test. I'm gonna give you the ratio test formally here in a minute, all right? But before we dive into ratio test, we're gonna get some definitions out of the way. So given an infinite series, and remember, I'm not putting n equals 1 to infinity here. It's just implied. Consider this sum, which is taking the absolute value, all right, of the sequence. Right, this is the sequence. I'm looking at a new series where I just look at the absolute value of the sequence. Then, if that sequence with the absolute values converges, the sum without the absolute value is called absolutely convergent. All right, so there has to be some natural reaction to this. And I would hope it would be a natural reaction, is that if we're going to look at this sequence here and look at its absolute value, right, that turns all of the little pieces into positives, doesn't it? That means there could possibly be a series that we're given where some of these are not positive, where they're negative, right? And we have not really discussed that. We have avoided them completely up to this point. Is it possible to have a series that has negative stuff in it? Sure. I mean, I could define a series like this. Examples of series with negatives. So here's a first example. Sum n equals 1 to infinity of negative 1 over n squared. That would have a bunch of negatives, wouldn't it?
Could you have like alternating series too?
That's what we're going to talk about right after this. Yep, that's the next thing I'm going to put up here. So this one would be all negatives, wouldn't it? This would be negative 1 plus what? Negative 1 fourth, and then plus negative 1 ninth plus. Now, would this series converge or diverge?
It would converge for the P series after you do
Yeah, this is a P series, isn't it? But we didn't have the negative there before. But negative is a constant, right? So I can just pull the negative 1 out, and then it would be P series and it would converge, yes? Further, if I take the absolute value of this, right? Isn't that just this then?
Yes.
So looking at, let me not put the absolute value right here. The absolute value of negative 1 over n equals sum of 1 over n squared. Look at this definition, all right? Looking back at this one right here, this had negatives in it, right? This had negatives in it. If we take the absolute value of it, consider the absolute value of it, look at that series. Does it converge? Yes, it's convergent, which means that the original series we were looking at is called absolutely convergent. Right? That's called absolutely convergent. Now, I don't like the word absolutely convergent that much because it makes people think that's like the ultimate type of convergence, right? Like the absolute convergence. But it just means that when you take the absolute value, it converges. All right? That's all it means. So here's an example of a series with negatives. Let's look at a more interesting example of a series with negatives, which has an entire name for classifying these. These are called alternating series. Now, we talked about alternating sequences already back in 8.1. And what was it that we used to make a sequence alternate? -1 to the n, or n plus 1, or we saw it could be like different, like n plus 3. So an alternating series, all right, is a series that looks like this. Or you could have -1 to the n plus 1. So all that's different now is that we still have a sequence, right? A sub n. But now we have this -1 out front that controls the sign of the sequence. So can you write out what these terms would be? If I plug in 1, I get -1 to the n, or to the 1, which is -1 times a sub 1, right? And I'm assuming that this is always positive. So I would get -a sub 1 plus
A sub 2.
squared, so positive, so a sub 2, then minus a sub 3 plus a sub 4 minus a sub 5, and this would go on forever, right? It's an alternating series. It switches signs. Yes? This one, the only difference between this and this one is what? The first one's positive, next one's negative, then positive, then negative, and so on and so forth, right? In either case, these are called alternating series. All right? So let's take a look at a new alternating series and see if we can figure out what it does. Convergence or divergence. So here's an example, a specific example. Does this converge or diverge? Let's write out what it is first. -1 plus a half minus a third plus a fourth minus a fifth. Are y'all agreeing with me? That's what that is.
So it diverges?
Well, that's what we're
Converges to
asking.
zero.
Does this does what convert? What converges to 0?
The series?
Does the series? Be careful.
All the way to sequence.
Okay, you're getting the sequence and series mixed up. Remember.
Yeah, I've always had that.
Okay, so yes, I agree that the sequence is converging to 0. This is going to 0. The sum of all of them, I don't know. So what do you think? Diverge? Is that what you said?
I was going to say the sequence converges to 0.
The sequence converges to 0. What do you think about the series? What does it look like? Okay, it does look like a p-series.
Oscillating, but it's still going towards the zero. If you take that n value,
It's not too serious.
Yeah, it's not exactly a p-series, right? Doesn't it look like the harmonic series?
Yeah.
1 over n, which is a p-series. Right? Isn't 1 over n harmonic? But it's also a p-series with p being 1, and that diverges, and harmonic series diverge. So this looks a lot like this harmonic series, right? What does this one do? It diverges. You would think maybe that diverges. Maybe, right? Well, let's try something here. Let's take the absolute value of it first. The absolute value of the inside gives you 1 over n, doesn't it? That negative 1 alternating no longer matters.
Yeah.
And this is harmonic. And it diverges, right? You agree,
Because these are mono P series.
right? This is harmonic, it diverges. Does this mean that this diverges?
No.
No, does not mean that.
Absolutely.
So look at the definition I put up on the board a second ago. I said that if you're looking at a series and then you take a look at its absolute value and that series, if that series what? Converges, we call that one absolutely convergent. But if this diverges, we're not going to say that's absolutely convergent. So the question remains, does that converge or diverge? Well, we have a test, all right? And it's your next test. It is on here. It's the second from the bottom. It is called the alternating series test. So this is an open question, okay? We don't know yet what this does. The alternating series test, which the name of the test kind of tells you when you should use it, right? When you see an alternating series. And you can only use this on an alternating series. You can't use this on a regular series. And the test goes as follows. If you've got this and they put n up there, but this could also be n plus 1, okay? So one or the other, doesn't matter what it starts with. It can start with a negative or a positive, okay? That's irrelevant. It's just that it does switch signs. So that's what we start with. The test says, what? It converges if, what's the if? What do we have to have happen?
If it equals 0?
1. I'm going to write a little different. A sub n is greater than a sub n plus 1. And number 2, the limit as n goes to infinity of a sub n equals 0. Now this is interesting because it's saying that this test says that if you have an alternating series, there's only 2 conditions that have to hold for you to be able to say it converges. The first condition is that the sequence is what? The sequence is what? Decreasing. And the second condition is actually the nth term test, right? But you know how we used to say in the nth term test, if we got 0, it meant nothing? In the alternating series test, if it goes to 0, it gives us convergence. All right? Yes?
Is it going to infinity or 0?
0. This right here? Oh, yes, thank you. This is infinity. Pardon me. Good catch, good catch. Now, we're not going to go into necessarily why the test works, all right? We're just going to believe that it does for now. Yes? So keep this in mind. This is a big deal. This is what we don't want to keep on getting confused on. If I give you a general series, here it is, all right? And you do this right here and you get 0, it's inconclusive, right? Test fails. But if it's an alternating series and you get 0, you're on your way. You just have to show one more thing, that it's decreasing.
So,
Okay?
oh, so you have to do, it's like the interval test, you have to meet those qualifications?
Yes.
Okay.
But in this case, we have to meet the qualifications, and if we do, we're done.
This works. Okay.
Yes. But it's only testing for convergence. If these fail, that doesn't mean divergence. Yeah. Or else it would say if and only if. But hey, that's okay because look, what if that second one fails? What if that second one fails? Then it just passed the nth term test. So it diverges. You go back to the very beginning and you're like, well, wait a minute, if this, I've got to be looking at this anyway, right? or else there's no sense in me to even be doing the problem. If this doesn't go to 0, I was done to start. I know, it's a little weird. All right, so let's go back to this problem here. If you could here, please identify a sub n for me. What is a sub n in this problem?
Negative 1 to the n over n.
Close.
Negative 1 to the n times 1 over n.
Closer.
Negative 1 to the n times n to negative 1. No.
Close still? I don't know. 1 over n. Okay, look at the formula. Negative 1 to the n times a sub n. The part that's away from the negative 1 that's alternating is the part that you're considering a sub n. All right? Understand? So when you rewrite this, this is negative 1 to the n times 1 over n, right? That's what that is. This part right here, the part that does not have the negative 1, is your a sub n. And that's the thing that you have to show is decreasing. That's the thing that you have to show goes to 0. All right? You don't care about the negative part for the alternating series test. You don't take it into consideration. But you need the negative 1 to the n to even be able to do the test, right? Okay. So let's do alternating series test. I'm just going to write AST. Yes, what? Huh?
So we have to get it to that formula, like the geometric series one that we did?
No, you just peel the negative 1 off, whatever it is. It's just remove the negative 1 from it. What remains is your a sub n. Okay, so alternating series test. I'm letting you know I'm doing it. I'm going to write down the two conditions that I need. I need a sub n to be bigger than a sub n plus 1, so I need decreasing. And number 2, I need the limit as n goes to infinity, I almost did it again, of a sub n to be equal to 0. Which of those you show first is up to you. So I'll start with the first one. So how about the first one? I'm checking to see if this is true. This is 1 over n greater than 1 over n plus 1. Do you all agree? That's that statement written out. And if you just do a quick little cross multiply, you get 1 is bigger than 0, that checks. The first condition is met, so I can continue. Second condition. What's the limit as n goes to infinity of 1 over n? 0. Check. Therefore, this converges. Therefore, three dots like this. Therefore, I'll write it like that. I could have written it like that. Converges by the alternating series test. That's kind of interesting, I think it is, because if you do the harmonic series without alternating and you just do 1 plus a half, plus a third, right, plus a fourth, if they're all positive, it diverges, right? But if you put alternate and make some of them negative, it's going to converge.
We can't tell what it converges to.
We don't know what it converges to. Yes.
Could you like compare it to like 1 to the n times 1 over n, and then take the 1 out?
Compare it to 1 to the n over. You might be able to do a comparison test. My recommendation, though, is anytime you see an alternating series test, think this, because those two conditions are relatively easy to show. And remember, this right here, if this inequality is messy, what's another way you could show this? The derivative is negative. Yes?
Wouldn't it be smarter to do the second test first? Because then.
I mean, that's why I said you can do either one. It's up to you. Yeah, it's up to you. I said I'm going to do this one first. I knew already this was going to go.
Yeah.
You know, like I kind of knew that to begin with. Another definition. If you have a series that is convergent, but this is divergent, then the original series is called conditionally convergent. Can somebody give me an example of a conditionally convergent series? My hint is that we just did it. Yes, the last one. The last one is a perfect example of this. If we look at the original series as being this one, right? We know that this one converged, right? By the alternating series test. We showed that. This one converged. Check. But when we took the absolute value, I forgot the n here, sorry, n. Absolute value. This equals sum 1 over n, and this is divergent, right? Yes? Then we call what absolutely conditionally convergent?
The original.
The original. This is then called conditionally convergent. That's a definition, all right? Absolutely convergent means that if the absolute value converges, then this is absolutely convergent. Now look at the last thing on here, and it's a test. It says if the absolute value converges, right, then the series itself converges. Yeah? So let me give you an example of that one in action. What about this? Does this converge or diverge? What could we use to figure out this converges or diverges?
Absolutely.
We could do the alternating series test, right? Or we could try that last thing there. Take the absolute value of this, which is just 1 over n squared. That's P series. P is 2, bigger than 1, therefore converges, right? This last theorem here, and they don't have a name for it, okay? But the last one says that if the absolute value of the series converges, then the original series converges. Make sense? Just don't confuse that with the conditionally convergent. Conditionally convergent is a series that converges, but when you take the absolute value, it doesn't. Right? So
Will you be okay with that answer on the test?
pardon?
Will you be okay with that answer on the test? Conditionally converges if we show it, obviously? Or is that not the answer?
Well, I'm always going to be asking you, does it converge or diverge? But the book on some of the homework, it asks, does this converge absolutely? So you take the absolute value and you see if it converges, right? Or it'll say, is it conditionally convergent? So conditionally convergent, you need the original one to converge and the absolute value to diverge. I know this is a lot to kind of get in order in your head, because there's, this whole idea of if the test doesn't work, it doesn't mean the opposite happens, right? So what if I tell you this? What if I give you a series? I'm not going to give you a specific one, but what if I tell you this? I give you a series, we don't know what it does, and I tell you that the absolute value of it converges. What would you tell me about that? That must converge, right? In fact, it's absolutely convergent. Because if the absolute value converges, that converges. Understand?
Yes.
So, different scenario. What if you don't know this, and I tell you that this diverges? You You can't say anything.
You don't know what that one does.
That's right. You don't know what that one does. Okay? So this would remain a question. This one would say that that one, what converges. Okay, let's move on. Maybe do another example. See if I've got another example in here. Yes?
So then if that platform converges but the absolute value diverges, it's conditionally.
That's conditional convergence. Yep. All right, so how about, that's kind of a lame one. No, there's a few of you here still.
You lost your followers.
No, there's still 2 that were out today, 6, so yeah. How about this as an example? Sum
So many people in here.
n equals 1 to infinity of -1 to the n times n squared over n cubed plus 1. Let's talk about some of the paths we could take here. Maybe the first thing we would do is like an n-term test. But when you do the n-term test, just look at this piece right here. Does that go to somewhere other than 0? No, that goes to 0, right? So n-term test isn't going to work.
It does help if you're in AST.
Yeah, but if we do the alternating series test, that's something we're going to need, right? And so we've already kind of mentally shown one of the 2 conditions. So the only other thing we need to show is that that's a decreasing sequence. Now that's one train of thought, okay? And that's the one I prefer. The other thing we could do is we could take the absolute value of this, right? What's the absolute value of that? That's n squared over n cubed plus 1. Do you know what this does?
Like 1 over n, so it diverges.
It looks like 1 over n, so you could do a comparison test now and figure out what that does. And if you did that, you would figure out that that diverges, which would tell you nothing. Because if the absolute value of this diverges, you don't know anything. Understand? That was close to the quiz. I had n squared plus 1 on the top, right? And 3n cubed plus 1 on the bottom. Okay, so I think alternating series test seems like the most natural thing here. So I'm going to go alternating series test, 2 conditions. Let's show the decreasing first, because we kind of already know that it's going to go to 0 when we take a limit. You want to set up the inequality here? I don't. I just want to do a derivative. That's what I'm going to do. I'm going to say, forget that. I'm going to define my function f of n to be just the part we're interested in. Look, the inequality right here would probably work out, okay? But I can do a derivative faster, I think. What's the derivative of this? Plus, it's good practice. 2n n cubed plus 1 minus 3n squared times n squared over n cubed plus 1 squared. Quotient rule. Derivative of the top times the bottom minus derivative of the bottom times the top. No?
Wait, why are
Did
they?
you do L'Hopital? You said limit, right?
No, no, no. I'm seeing if the derivative is positive or negative, right?
Okay.
To see if it's decreasing.
Oh, okay. I was confused on why you were doing that.
Yeah,
Yeah, instead of showing it's decreasing with an inequality, I've chosen to show that if I look at it as a function, the derivative is going to be negative.
Thank you.
But you could have done that if you wanted to. Is that right, though, derivative-wise? Yes? Okay, so let's clean up the top. It's 2n to the 4th plus 2n minus 3n to the 4th over, the whole thing's positive on the bottom, right? Guaranteed? So I don't even care about that. And on the top, when I subtract, right, these two together, I'm going to get 2n minus n to the 4th over a positive number. And then on the top, I think it's obvious that that's negative, right? But if I factor an n out, it's even more obvious. Because if n is a positive number, right? That's positive. And what about this number right here? It'll be negative as soon as n gets past 1, right? Because at 1, this is positive. So eventually, this is going to be decreasing. So this is actually less than 0 when n is greater than 1, which is good enough, right? Do you all understand that? Okay. Maybe the inequality would have been easier. Who knows? But again, I want you to see that this is in our toolbox. We can pull that out and use that when we need it. What's that? You can do what?
Like, you just take derivatives? I thought you had to take a limit for the other one, for the other.
Do you prefer this?
What?
We're just trying to see if it's increasing or decreasing.
I think you're confusing what I'm doing.
Yeah.
I'm in the alternating series test. I'm trying to show the first condition, which is to show it's decreasing, a decreasing sequence.
Okay.
But instead of looking at it as a sequence, I'm looking at it as a function, and I'm showing the derivative is negative, which shows me that the function decreases, which means the sequence decreases. Yes?
You prefer this way?
I don't have a preference. If it's something I don't want to take the derivative of, I prefer that way. But if it's something pretty clean, I like this. I like this because you're practicing taking your derivatives, so you're getting better at that, and then you're also having to just number sense, thinking through like what things are going to wind up being. So for me, I like that more it's more constructive in terms of what a student is being exposed to when they do that. All right, so what's the conclusion? We didn't show the second thing. The second thing we had to show was that the limit as n goes to infinity of n squared over n cubed is 0, but it is, right? Yeah. I could do L'Hopital, but I'm not even going to show it. You're welcome. All right, we good?
So I have a question.
Yes.
So taking the derivative, I mean that that's more beneficial if you're using something like a comparison test. Like let's say you're trying to figure out what to constantly keep comparing.
Wait, start over?
Like when you're doing the comparison test,
Uh-huh.
and you know you have to figure out is one increasing or one's decreasing. So wouldn't that be more beneficial in that sense versus trying to figure out? Like let's say you get some function that you don't want to have to do the inequality.
Mm-hmm.
So you have to put it here, but add a constant here, but not here.
When you're doing comparison test, your inequality involves two different things, right? The one that you came up with and the one that you're started with. So you came up with that comparison. You could not do derivative in that sense. Because on comparison tests, you're not trying to show something is decreasing or increasing. You're trying to show that one is bigger than the other, right? So you could not use that. We used this same method of taking derivative when you were doing integral test. That's when you have to show that the sequence is decreasing. Good question. Good question. Let's do one more. Sine to the n over n to the fourth. It converges, that's it?
Oh, no. Yes, this
We're talking about the last one, like basically the last one.
That's what?
The last one.
Oh, the last one converged. Sorry, I didn't conclude. So last one converged by the alternating series test. What about this one? Is this an alternating series? No, because it doesn't have the -1 to the n. Does it change signs, though? Yeah, because sine we know is going to be positive and negative different times and 0 sometimes, right? And so it's possible that that top is going to be positive and negative just throughout the sequence, right? So it's not a true alternating, right? So we can't use alternating series test. Do you understand that? What's that? Ratio. Well, we haven't done it yet, right? What is your instinct telling you? Do you think this converges or diverges? You think it converges? I'd say that's probably fair. If it converges, then maybe we should check to see if it's absolutely convergent. Look at this. If I can show you that that converges, then that would be enough to say that converges, right? Because if the absolute value of this converges, then it by itself will converge due to the last thing on this sheet, right? But you'll hear that?
Rain. It's not rain.
That's not rain? What is that?
No, it's like really light outside.
I know.
No, it's.
I was thinking the same thing.
It got quiet because the air cut off.
What? Is that what it was?
Yeah.
Okay.
That's what I thought too.
All right, so what I'm going to do to try and show that this converges is I'm going to first sign in. I don't need the absolute value around the bottom, right? Because n to the fourth is always positive, so that's the same thing. But I still don't really have any way of doing this, like no integral test, it's not geometric series. There's a lot of things I don't know, right? I can't work with here, understand? So, but it looks a whole hell of a lot like something I am familiar with, and that is this series, right? So what I'm going to do is I'm actually going to run a comparison test right now, comparing this to this, not this to this, right? Understand?
Yes.
The reason why I want to choose this to run against this is because I can guarantee you that all of these are positive, right? This is always positive, and this right here is always positive. So let's do a comparison test. Well, what do we know about this one over here? This one converges because it's a p-series. P is 4 greater than 1, it converges, all right? So what is the inequality that I must be able to show you?
That A sub n is
That this one is always less than this one, right? If I can show you that, I'm done? Okay, so I want to show that absolute value of sine of n over n to the fourth is always smaller than or equal to 1 over n to the fourth. Right?
Yep.
Multiply both sides by n to the fourth, and what do you get?
Sine n is less than
Absolute value of sine n is less than or equal to 1,
which is true.
which is true.
Never
Right?
past one.
Sine, sine we know is bounded between -1 and 1, right? So if I take the absolute value of it, of course, it's still going to be less than or equal to 1. So this is always true for all n, isn't it? So since this checks, the comparison test works.
Yes.
That means that this converges, right? That means the absolute value of that series, right, that sequence converged, which means that that converges. You see that?
That was like 2 tests.
It was almost like 2 at 1. I started with something that didn't quite alternate, so I couldn't use the alternating series test. But I recognize that if I take the absolute value of this thing, if I can show this converges, that automatically converges. And doing a little bit of tweaking on the absolute value, I could somehow control that top. I know that it's never going to get bigger than 1. Be clever, pick my comparison, show the inequalities true. This converges, which forces this to converge, which forces that to converge. Understand? Okay, that's the way it works. Is that a question? Okay. All right. Yeah, so how would we write this? I mean, if we were going to really want to be good mathematicians, we would have this. We'd have something like, I'm not going to do the n equals 1. N to the fourth converges, which implies that this converges by comparison test, which we showed above, right? Which equals the absolute value of this. Which implies that converges. Because if the absolute value of the sequence converges, then the sequence converges, well, the series with that sequence converges. All right, we need to continue, move on. All right. I'm going to get to ratio tests, but I've been kind of like flipping a coin in my head whether or not I want to mention the next thing. I normally don't mention this, but I heard some students out in the hallway yesterday talking about it. Students not in this class, in another Cal 2 class. And I said, you know what? I don't want any of my Cal 2 students to hear them talking and not know what the hell they're talking about. So I'm going to mention this, all right? This is called the alternating series test estimation theorem. This theorem is a way to estimate the sum of an alternating series. So I've conceded, and I've told you to please concede also, to the idea that all we're doing is finding out whether or not things converge or diverge. The only things we can actually find sums of and figure out what they add up to be are which type of series. Geometric and no, telescopic ones. Those are really the only ones we can do, right? For geometric, as long as the absolute value of r is less than 1, we've got a formula for it. Telescopic, we have to run through all the calculations and get things to cancel, and at the end we take a limit and we get an answer. Other than that, it's just converge or diverge. That's all we've been able to do. This theorem gives us a way to estimate what the sum of an alternating series is, but it only works for an alternating series. And you may not be happy with the word estimate because you probably want to have the exact answer, but you can estimate it as closely as you ever want to the true answer. All right, so let me write the theorem out for you. I'll write it just the way it appears in the book. Okay, if capital S is equal to the sum as n equals 1 to infinity of negative 1 to the n times b sub n. They're using b sub n instead of a sub n, all right? I'll switch to a sub n so we follow the same notation, because that's what we've been using, right? A sub n? All right. If that is the sum of a convergent alternating series. So we are assuming that we are looking at an alternating series that converges. We know it converges, which means it actually adds up to some number, right? That number we're calling S. So if we have this happening, which it doesn't always have to happen, right? You can have a divergent alternating series. So, but if it adds up, and part 1, 0 is less than or equal to a sub n plus 1 is less than or equal to a sub n, which really saying, what is this really saying?
If a sub n is greater than 0.
Decreasing? That's the way they wrote it in the book, but isn't that what that's saying? The nth term is bigger than the next one. But they're both positive, right? So if that's true, and the second thing is that limit n goes to infinity of a sub n equals 0. Aren't those exactly the conditions for the alternating series test? Okay, so if we have an alternating series that converges, which means those two have to be true, then here's the conclusion, all right? I want to write it up here. Then capital R sub n, which I haven't told you what that is yet, the absolute value of that, is equal to S minus S sub n, but that's less than or equal to a sub n plus 1. Whoa, what? Okay. What is capital S?
That.
It's the sum of our infinite alternating series. The difference between that and what's S sub n? The partial sum. That means if we only add it out to a certain point, right? So if we go and we add like the first 100 of these up, then that would not be the whole thing, right? We would be off by some. This is that difference, right? That's the difference between the true sum and a partial sum, which we will call the remainder, the remaining part that's wrong, that we're off by. Yes? This would be what we're off by. We're guaranteed through this theorem that how much we're off by must be smaller than a sub n plus 1. Now, that's crazy that this works this way, but that's why it's a theorem. It's been proven that this is true. Let me show you this in action, all right? We're going to have to refer back to this. If I say it in another way that makes maybe a little more sense in English, is that if we add up the first 1,000 of these, right, and stop at 1,000, I guarantee you that I'm only off by this sequence, okay, the sequence right here, sorry, this right here, that right there, me plugging 1,001 into it. Whatever that number is bigger than how much I'm off by. If you understand that, what I just said, it's pretty amazing that that's the case.
It's kind of like what you told us you fill it with butter, you fill it with smaller amounts of water, but it's never going to overflow.
Yeah, I guess that's, okay. Yeah, you know what? Maybe I can do an analogy with pictures.
It's like you adding a cup of water and then a small cup of water and then a drop.
I'm going to go with that. I like that idea. Okay, so let's say that we have a series that's just going to add a bunch of things up together, right? Now, this is an alternating series, so we're adding, taking away, adding, taking away, adding, taking away. But we're saying it converges. That means that it does add up. If I could sum to infinity, it would be finite. Understand? But I'm only going to sum up part of it. I'm going to sum partially, so I'll never get to the true sum, right? That sum, I stop at n, right? The next time, so this stops at n, right? So I'm adding, I'm stopping at n. Then the next time I would add the next one, right? That next one has a size to it. Got it? The size of the next one would just be this little tiny layer that goes on top of that, right? Okay, the size of the next layer is bigger than how much I'm off by. It's crazy to think of this. Yeah, okay, but I'm going to not do that. Let's just do an example. All right, find the sum n equals 1 to infinity of negative 1 to the n over n, correct to 3 decimal places. All right. Now, trying to think of which way I want to approach this. Let's write out the first few of these. We said that this was what? Equal to negative 1 plus a half. Shit, this is going to take forever. Let's do this. Let's go n squared. Or let's go even faster, n cubed, okay? So this will be 1, what, 1/8 would be next? Minus 1, what, 27th plus 1/64th minus, get your calculators out. Yes, but we're going to convert these all to decimals. All right? Okay, so 1 over 125, right?
216.
Plus 1 over what?
216.
216? And I keep going, right? So this continues, dot, dot, dot. Remember that if I ever stop, right? If I ever stop,
At the end.
this will be n, right? What's the next one after n? Let's do one more. N plus 1, which for us would be, what, 7 cubed? 343? Right? This would be the n plus 1 right here. Do you agree with that? Yes? So if I stop my sum right here, this would be my nth partial sum. Agreed? What we know is that how much we're off by, which is the true sum minus my partial sum, must be less than or equal to a sub n plus 1. What's a sub n plus 1? This right here is a sub n plus 1, isn't it? Okay, so let's see how much we're off by here. Tell me, what's 1 over 343 as a decimal? 0.002915, right? Understand? What I can tell you right now is that this sum is within this much of the true sum so far. If I go out a little further, it's going to get even better. All right? I want to see how far I need to go out so that my first 3 decimal places are correct. So what I'll do now is let me start this over, and this time let's let this one be n right here. Okay, if I do that, what's the next one? Plus 1 over, what, 8 cubed? What's 8 cubed? 512? What's 512? What's 1 divided by 512? 195. So if I take my sum now, see, I hope you're following this, I really do. If I take my sum now and I stop at the next one, right here, if I stop there, how much am I off by now? This much, right?
Yeah.
Did the third decimal point change?
Yeah.
Yes.
It did, which means that this is not far enough. I need to go and keep going until that third decimal place is locked in.
So like keeps going 1, it keeps being 1.
It can't switch from 1 now. It's got to stay at 1
How many times do you have to go though?
until this doesn't change. Let's go one more, okay? Let's go one more. Maybe it'll help you. Maybe it'll help you if you do this. What's the difference between these two? Subtract. Go 0.002915 and subtract from it 0.00195. What's the difference? Whoa, did I do that right? Yeah? It's 0.000965, right? That's the difference between those? Yes?
Yes.
Okay. Just keep that in mind. Let's go to the next one. If I were to now, I'm going to have to write this all again to -1 plus 1/8 minus dot, 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 dot. I get all the way out to, and now I'm going to stop at 1 over 512, right, plus. The next one is 1 over, what, 9 cubed?
729.
729. So now I'm stopping here, right? That's my S sub n. What's this one right here? 1 over 729.
The derivative
1.00137, right? 137?
Yeah.
Okay, and the one before it was 0.00195. What's the difference between those two?
4th decimal place.
Right?